So, hello and welcome. This is my little video about my DIY temperature controlled Astrocamera cooling solution. And I'm doing this video because I did something different than others on YouTube. The other types of cooling they did not control the temperature, they just cooled the camera, like with just a heatsink or a heatsink plus a Peltier device. So what I did is I took an AMD CPU cooler together with a Peltier device sandwiched beneath the camera and the cooler, a temperature sensor put directly onto the camera between my insulating material, like some stuff I had layering around. Here you can see it. And an Arduino that's inside this box with some LEDs for temperature display purposes, and a PWM MOSFET driver also located inside this box. Code-wise, I use for the Arduino is basically just a PID driver, a PID controller, and for those who don't know what a PID controller is, I just generated a quick explanation from ChatGPT. I'm just reading that aloud. Like, imagine you want to keep your room at 22 degrees Celsius using a heater, and the PID controller is in charge. And the P, the proportional, it looks at the current temperature error, which is how far the actual temperature is from 22 degrees Celsius. If the room is at 20 degrees Celsius, like 2 degrees too low, it cranks up the heater proportional to that difference. Bigger error equals more heat. But it's a blunt tool, so alone it might overshoot and roasts you. The I, the integral, it remembers all the times the room has been a little too cold. If the room has been stuck at 21.9 degrees Celsius forever, the I part builds up and adds heat over time to fix that tiny persistent error. Without it, you would never quite hit 20 degrees Celsius. The D part, the derivative, it's like a fortune teller. If the room is heating up too quickly and looks like it will overshoot 22 degrees Celsius, D will reduce the heat power early to avoid temperature roller coaster. In short, the PID keeps adjusting its heater so the room gets to 22 quickly, stays there and doesn't turn into a sauna or an ice box. And while building this, I had the following problems. Maybe I want to tell you before you run into them. First thing is, you need proper insulation for your camera. It saves you a lot of power, and if this thing starts cooling, condensation builds up and ice. So you want to try to cover almost everything of the camera so that it doesn't get into contact with direct air and you won't have that much condensation or maybe water leakages into the camera itself. So this reduced the risk by a lot, I believe. Second thing is, the heatsink. Go as big as possible with this. This will increase your efficiency of your Peltier device. Do not go too small with this one. But also keep in mind, if you go bigger, your camera gets heavier. And maybe this is a problem with your telescope. So you need to find a middle ground. Go as big, but do not go too heavy. And third thing is, if you use a field flattener, you need to 3D print a T2 to T2 extension tube. It needs to be plastic, because if it's metal, this extender will also get cold and dew will form on this one. And this is also reducing efficiency, and it will also cause problems with condensation and ice. And to reduce this risk, plastic is a great insulator, and you will need this one too. And well, let's just start this thing up to see what it looks like in action. For powering this thing, I just have a 12-volt power barrel jack and a step-down converter to 5-volt, so I could also power this with USB. So when powering this thing up, my device gives me a 30-second window where I can set the temperature. Now the fourth LED is blinking, and in binary this is an 8. And I multiply this by 2, so I have the value of 16. So my set temperature is 16 now. And after the 30 seconds, this device tells me how far it is from these 16 degrees Celsius. This is a binary 1, 2, 4, binary 6. So 6 plus 16, it's 22 degrees. So its current temperature is 22 degrees, and it needs to cool 6 degrees Celsius. But now I have to put it back in this temperature sensor so it gets its feedback. Here we go. And the temperature is already dropping. Just 1 degree left and 0. Maybe it will overshoot now because it got put in full power while the sensor was outside of the camera. But seems like it is quite stable right now. Now it did overshoot. It is now 1 degree too cold. And now the PID controller will do its things and pendle in just around this temperature. My observations were that it is very stable. If I produce a large temperature difference, like powering the camera right now, it just has an error about 0.1 degrees Celsius. So it reacts quite fast and it is precise enough for this purpose. And the conclusion of all of this is, do not just cool, go the extra step and build a small controller. After this, there's only a small difference to its bigger brother that's twice the price. I bought the camera for 500 euros and the bigger brother that is already cooled was selling around 900 euros used, or 800. So it's definitely worth it if you want to save some money, or if you already have all the parts laying around. Yeah, it is a bit more work, and you have to read in more articles about the stuff I used here, like the MOSFET driver, the PID controller. But it's definitely worth it. You will learn a lot, and it's a cool project. And in the end, it has a real purpose. And you can be proud of yourself. Yes, so that's it from my part. I hope you found this interesting, and helpful. If you have questions, just leave a comment. I try my best to answer them, and if you need the code, I post it into the description. And yeah, see you.